It says that the line integral of magnetic field around any closed path in free space is equal to mu naught times the current enclosed by that path. The direction of magnetic field is tangential to the circle. You can observe this is my magnetic field, it is always tangential to the circle. The right hand rule says that if we hold the wire in right hand, the thumb points the direction of current and the curl fingers signifies the direction of magnetic field. Hello everyone, welcome to session 3 of chapter 4 Moving Charges and Magnetism. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Dear children, in this chapter we are studying about the properties of magnetism and how does the moving charges create magnetism around it. So let's begin the session by studying Ampere's circuital law. We are already familiar with Biot-Savart's law. We are now studying about one more important law, that is Ampere's circuital law. So you will have a question in examination like state and explain Ampere's circuital law. What is the statement of Ampere's circuital law? It says that the line integral of magnetic field around any closed path in free space is equal to mu naught times the current enclosed by that path, which means Ampere's circuital law can be applicable only for closed surface. So the line integral of the magnetic field, that is B, of any closed path in free space is equal to mu naught times the current enclosed by that path. So this is the statement of Ampere's circuital law. So if the statement you are finding it difficult to understand or to remember or to recall in examination, you can just remember the expression. The closed surface or the line integral of the magnetic field, around any closed path in free space is equal to mu naught times the current enclosed by that path. Here mu naught is nothing but the permeability of free space. I is nothing but the current and B is the magnetic field. So this is the statement and expression for Ampere's circuital law, which is very important examination point of view. So let us now derive an expression for magnetic field strength of a current carrying conductor which is straight by applying Ampere's circuital law. Now we understood what is Ampere's circuital law, what is its statement, what is its expression. Applying that, we are now finding the magnetic field strength due to a straight current carrying conductor in a magnetic field. So now let us consider XY as a straight conductor which is of a larger length, and R is the radius. Radius means P is the point where we are finding the magnetic field. So let us say that the magnetic field here is parallel to our line element, that is DL. So let us explain the diagrammatical representation now. XY is a straight conductor of an infinite length. What is I? I is nothing but the current throughout the wire, and P is the point which is at a distance R from a straight wire. Now DL is the line element of the Amperian loop. This is an Amperian loop which is a closed path. DL is a small line element and B is the magnetic field which is at point P. R is nothing but the distance between straight conductor and the point P, which is nothing but the radius of Amperian loop, the closed surface. Now suppose if we draw a circle of radius R such that the straight conducting wire is perpendicular to the plane. You can observe here the straight conductor is perpendicular to the plane. Suppose if this is my Amperian loop, then my conductor is perpendicular to the plane of circle and it is passing through its center. You can observe here the wire is passing through the center of Amperian loop. The direction of magnetic field is tangential to the circle. You can observe this is my magnetic field, it is always tangential to the circle, and it is also parallel to DL, the line element of Amperian loop, and the magnetic field are parallel to each other. When they are parallel, we know theta is equal to what? It is nothing but 0 degree. So let us apply Ampere's circuital law before applying theta value and all. Ampere's circuital law says that the line integral of magnetic field around any closed path is equal to mu naught times the current, that is B into DL is equal to mu naught I for a closed path. This is my Amperian circuital law. So now that can be written as, since it is a dot product between B and DL, it is B DL cos theta is equal to mu naught into I. Now what is the value of theta? Since B and DL element are parallel to each other, the theta value is 0. What is the value of cos 0? It is nothing but 1. But we need to integrate all the line elements of the Amperian loop, that is why, and the magnetic field is constant throughout, so we can write it as B line integral of the line element, which is equal to mu naught into I. And now if we integrate if this is my circle or circular Amperian loop, this is the dl, which is the small line element. So if you integrate all dl elements, we will just get the circumference of the circle. So the circumference of circle is nothing but 2 pi r. So instead of dl, when we integrate, we'll get 2 pi r. So we get B into 2 pi r, which is equal to mu naught into I. Or we can just write it as we are finding the expression for magnetic field strength due to a infinitely long straight conductor, and hence it is B is equal to mu naught into I divided by 2 pi r. So this is the expression which helps us to find the magnetic field strength. Let us move on to the next important topic, that is the solenoid and the toroid. So what is a solenoid? Solenoid and toroids are the pieces of equipments which are used to generate the magnetic field. We do even have a synchrotron which utilizes both solenoid and toroid, which is helpful for generating high magnetic fields. So solenoid is basically an equipment which is used to generate magnetic field. So this is how we can represent solenoid in a diagrammatical way. A solenoid is nothing but a cylindrical coil which consists of n number of turns of closely wound insulated wire. You can observe here, this is a wire which is closely wounded on the cylindrical coil. So this is called as solenoid, and the long solenoid is nothing but the solenoid whose length is very big or very large. We will call it as a long solenoid. So this solenoid consists of a long wire which is wound in the form of helix. Since there are n number of turns, each turn is closely spaced with the neighboring turn, and each turn is regarded as a circular loop. So here, since it is a circular loop, we have already studied with what is magnetic field around the circular loop, so we can just apply those concepts for each and every turn. So when current flows through the solenoid, the net magnetic field or the total magnetic field is nothing but the vector sum of magnetic fields due to each turn. So the magnetic field due to current through a straight conductor of infinite length is given by mu naught into I divided by 2 pi r, which is just now derived previous slide. So from this expression, it is clear that the magnitude of magnetic field at every point on a circle of radius r is same, because we have considered a circular coil of radius r. So at every point the magnetic field is tangential to the circle. Since it is tangential, the magnetic field at every point on a circle of radius r is B is equal to mu naught into I divided by 2 pi r, because we know that the magnetic field is tangential to the circumference of circle. But how to find the direction of magnetic field? The direction of magnetic field due to a current in a straight conductor can be found using right hand rule. So suppose if I hold the conductor like this, with the help of right hand rule, we can find the direction of magnetic field. What does it say? The right hand rule says that if we hold the wire in right hand, the thumb points the direction of current and the curl fingers signifies the direction of magnetic field. So we have studied about Ampere's law and Biot-Savart's law. Both these Ampere's law and the Biot-Savart's law can relate about the magnetic field and the current. But Ampere's circuital law holds good only for a steady currents which do not fluctuate with time. So these are some of the basic things regarding magnetic field and regarding an Ampere's circuital law. Our next important topic is force between two parallel current carrying conductors. So for that we need to consider two parallel current carrying conductors. The question may come like this in the exam: derive an expression for magnetic field strength due to a straight current carrying conductors or wires by applying Ampere's circuital law. For that, let us consider two conductors which are A and B. They are carrying a current I, and we will call it as IA and IB for the rods, for the conductors A and B respectively. Here F is nothing but the force between these two conductors, and D is nothing but the distance of separation. L is the small line element. So I hope the diagram is clear to everybody. To derive any expression, diagram is compulsory. So in this figure, AB are the two conductors or parallel conductors, and D is the separation between A and B. IA and IB are the current through conductor A and B respectively. What is the magnetic field produced by A on B? It is BA, and the magnetic field produced by B on A is B suffix B, and L is the length of line segment as I have shown already. Now, according to Ampere's circuitous law, the magnetic field produced by A, which means the magnetic field produced by the conductor A on B, is given by BA is equal to mu naught IA, because the current in the rod or in the conductor A which results for the magnetic field BA is nothing but, which is the field produced by A on B, divided by 2 pi d. Here we are not using 2 pi r because d is the distance of separation between two rods. So this is our equation 1. Now, due to this magnetic field, the magnetic force will generate between these two rods. Now let us find out what is the magnetic force on B due to A. That is the force on B due to A. That can be calculated as, we know the expression for force due to a straight current carrying conductor, that is ILB. F is equal to ILB. So IB is the current in the conductor B, L is the length, and BA is the magnetic field that is produced by A on B. So now we have BA term. Let us substitute this value in the equation. So what do we get? F1 is equal to mu naught IA. It is there in the BA expression, and here IB I already have, L I already have, 2 pi d we have. So we get F1 is equal to mu naught IA IB into L divided by 2 pi d, and the direction of this force is always towards the conductor, which means the direction is towards the conductor. Similarly, let us find the expression for magnetic field produced by the conductor B on A. So that can be written as B suffix B, that is magnetic field produced by B on A, which is nothing but mu naught IB divided by 2 pi d. Since it is about the conductor B, we have to take the current in the conductor B. And that is my equation 3. And because of this, the force will generate, or the force will be experienced by the other conductor. The force on A due to rod B or due to conductor B is F2 is equal to, again we have considered an expression for force, that is F is equal to ILB. So in the place of B here, since it is about conductor B, we have taken B suffix B. Or in the place of B, we can substitute mu naught IB, IA already I have, L we have in the above expression divided by 2 pi d, and we get mu naught IA IB L divided by 2 pi d, and this, in this case also, the direction of force is always towards conductor B, which means you can see here the direction is now towards this way. Since the directions of force are opposite, that proves Newton's third law, that is we can write F1 is equal to minus F2. Now the magnitude of force from both the expressions we get, that is mu naught IA IB into L divided by 2 pi d. When we consider a unit length, the conductor which is having a length of 1 unit, then the term L will become 1. So we get the expression F is equal to mu naught IA IB divided by 2 pi d. So from this we can define what is 1 ampere, or the definition of ampere can be calculated. How? So we have the expression F is equal to mu naught IA IB divided by 2 pi L. Here F is nothing but the force per unit length. We have considered a length which is equal to 1 meter. Suppose if the value of IA and IB is equal to 1 ampere and the distance of separation between two conductors is equal to 1 meter, then we get the above expression F is equal to 4 pi into 10 power minus 7 into, in the place of IA it is 1, IB it is 1 divided by 2 pi as it is, and the distance of separation is 1 meter. How do we get this 4 pi into 10 power minus 7? Because we know the value of mu naught by 4 pi is equal to 10 power minus 7, and we just want mu naught, which is 4 pi into 10 power minus 7. So now with the help of this, you can just solve. Pi and pi get cancelled, 2 ones are, 2 twos are, and we remain with 2 into 10 power minus 7 Newton per meter. So we get the value 2 into 10 power minus 7 Newton per meter. Now it is helpful for us to define what is 1 ampere. So ampere is defined as when the steady current is flowing in each of two infinitely long straight parallel conductors of a negligible cross-sectional area, when they are separated by a distance of 1 meter in vacuum, it causes a force between them, that is 2 into 10 power minus 7 Newton per meter length of each conductor. So the value, that is the value of force between the conductors, will be 2 into 10 power minus 7 Newton per meter, which we should not forget to mention in the definition of 1 ampere. So this is about the ampere circuital law and about the straight conductors which is carrying current and the magnetic field strength due to two straight current carrying conductors with the help of ampere circuital law. In the next session, let us learn few more interesting and important concepts. Until then, keep learning all of you. See you all in the next session. Thank you.